Hi everyone. The today's session topic is calculation of time and energy loss in transient operation. So during the drive transient operations, what is the time taking for the drive transient operation means transient operations may be starting, during the braking, during the speed reversal or speed change. All these are called transient operations of the drive. During the transient operations, if we calculate the time, we can find out the energy loss during the transient time also. So we need to find out the time. By using the time, we can find out the energy loss during the transient operations like starting, braking, speed reversal or speed change. So to calculate this time during the transient operation, we'll use the torque equation. The overall torque equation T is equal to TL plus load torque plus J into d omega by dt, torque due to the inertia, and TV, that is nothing but viscous friction coefficient, that is due to the frictional torque, and TC, Coulomb frictional torque, TW, windage torque, and TS is nothing but standstill torque. So to oppose this motor torque, the motor torque is developed to overcome all these opposing torques, which are nothing but load torque, inertia torque, frictional torque, Coulomb frictional torque, windage torque, and standstill torque. The standstill torque is equal to 0 when the drive is in operation. So we can neglect this one. Compared to the other torques like load torque, inertia, and frictional torque, your Coulomb torque and windage torque are very less. Hence, we can neglect this Coulomb torque and windage torque also. Generally, this windage torque is directly proportional to the speed square of the speed. That is nothing but windage torque is directly proportional to the omega m square. Windage torque is directly proportional to the omega m square, where windage torque is equal to k into omega square. We can neglect this one also as it is less when we compare to the first three components, that is load, torque due to the load, inertia, and friction. Okay, this Coulomb torque is independent of the speed, Coulomb frictional torque. So by neglecting that Coulomb torque, windage torque, and standstill torque, your equation will become T is equal to TL plus J into d omega by dt plus TV or TB. So here the TV, viscous frictional torque, is directly proportional to the speed, and windage torque is directly proportional to the square of the speed. So by removing this proportional, we can get TV is equal to B into omega, where B is nothing but viscous friction coefficient. Here by removing this proportional, we will get TW is equal to K into omega square. So your overall, by neglecting the TC, TW, and TS, we can get the equation as T is equal to TL plus J into d omega by dt plus B omega. Okay, so this is your torque. By using this torque equation, we need to find out the time, transient time, so that we can find the energy loss also. So usually the transient operations of the drives are called during the starting, braking, speed change, or speed reversal. These conditions of the drives are called the transient operations. So to calculate the time taken and energy dissipation in the motor during the transient operations, we need to use this equation to calculate the time. The torque T is equal to TL plus J into d omega by dt plus B omega. Here T and TL, motor torque and load torque. If motor torque and load torque are constants, and if they are proportional to the speed, that may be T is equal to 100 minus 0.1 omega m. That is one of the equation. In the problem statement we will see. With the problem we can understand in a better way. So if torque is directly proportional to the speed and load torque is also directly proportional to the speed and both are constants, then we can solve this equation 1 analytically, because these equations become first order linear differential equation. If t and tl are constants and which are directly proportional to the speed, then this entire equation will become linear differential equation, first order linear differential equations. We can solve this equation analytically. In case if t and tl are neither constants nor proportional to the speed, then this equation will become non-linear differential equation. If it is non-linear differential equation, we cannot solve it analytically, so we need to go for numerical methods to solve that equation. If t and tl in the problem statement, generally we don't have if we have t and tl are not constants, neither constants, not proportional to the speed, then we need to solve that equation by using the numerical methods like Newton-Raphson method or Runge-Kutta methods. Okay, so here during the transient operations, the final speed is considered as equilibrium speed. So your speed may vary from, or your speed is changing from omega initial speed omega m1 to omega m2, but your equilibrium speed is nothing but omega me. So theoretically the transients will be over at infinite time, because transients will exist forever. So transients will not die out. So it will take infinite time to die out the transients. But in practice, we'll consider that the transients will be over at 95% of the change in speed. At 95% of the change in speed, the transients will get over. That is our assumptions, and we can go ahead with the problems. So let us take, if initial speed is omega m or omega m1, and what is the equilibrium speed means. In practice, we will consider that omega equilibrium speed is nothing but omega m1 initial speed plus 95% of the change in speed, that is nothing but omega me minus omega m1. So this is nothing but transient time. So transient time means we will use this limits to calculate the transient time. Okay, so to reach the speed from omega m1 to omega m1 plus 0.95 times of omega me minus omega m1 is nothing but transient time. After that, your drive is in steady state. So that's what our assumption. So here calculate that the transient time and energy loss we can calculate by using this torque equation. Here torque T is equal TL plus J into d omega by dt. By neglecting that frictional torque, we can get the torque equation as torque T is equal TL plus J into d omega by dt. Here J into d omega by dt is equal T minus TL, because if we consider comparing to the low torque and inertia torque, even the frictional torque also it is less. That's why we'll neglect that frictional torque and we can proceed for the solution. So J into d omega by dt is equal T minus TL. From here dt is equal J into d omega by T of omega minus TL of omega m. So here torque, main torque as well as load torque, both are function of R is proportional to the speed. That's what we have considered and we are solving analytically. Okay, here by integrating on both sides of this equation, we can get the transient time. Transient time T is equal, J is constant, J into integral, the limits are omega m1 to omega m2. Speed is changing from omega m1 to omega m2. D omega m by T of omega m minus TL of omega m. So this is the equation to find out the transient time. So by that is nothing but here J by T of omega m minus TL of omega m over the speed is nothing but the transient time. Graphically we can represent that by considering J by T of omega m minus TL of omega m on y-axis, speed on x-axis. We can the area cover under this y-axis and x-axis is nothing but the shaded area is nothing but the transient time. Omega m1, instead of considering 0, at some place we are considering omega m1, and omega m is nothing but equilibrium speed. It will never reach to the equilibrium speed. That's why omega m2 at some other speed, the hatched portion is nothing but the area cover under the j into d, j by t of omega m minus tl of omega m and omega m. From this integration is nothing but area cover under that speed. So that's what we have graphically represented that. So by using that graph we can find out the transient time. Generally we'll use this equation in the problem statement. They'll give main torque as a function of speed, low torque as a function of speed, starting speed and equilibrium speed. To find out the equilibrium speed, they'll give some conditions, so that from the given data we can find out the transient time. Once if you find out the transient time, you can find out the energy dissipated during the transient operation. The energy dissipated during the transient operation is nothing but, generally power loss is nothing but I square into R. If we multiply with the corresponding time, here time is nothing but transient time. Energy dissipated during the transient time is nothing but integration of 0 to t I square into R into dt. It is nothing but I square R into t is nothing but the energy dissipated during the transient operation. Here R is nothing but the motor winding resistance and I is nothing but the current flowing through the winding. We know the current flowing through the winding and R motor resistance, motor winding resistance we can take from the given data, and we can calculate the energy dissipated during the transient operation. Okay, in this way we can find out the energy dissipated during the transient operation and also the transient time. So by using this equation, we'll see with the problems in further classes. Thank you all.